In this video, we're going to talk about what a function is, right? And so what this course is pretty much about is doing things with functions. And so before we can do things with functions, we need to get very familiar with what functions are and some different types of functions. And that's what we're going to talk about today. One definition, sort of informal for a function, is a rule that takes certain numbers as inputs and assigns to them exactly one output number. And so sometimes people like to do a diagram as such as this, where I have a set of numbers in one set, and we assign a rule. So we take those input numbers, these are our inputs, apply a rule, which we can call f or function, and then we get some output values. And it just so happens that in order for this to be a function, each input has to get assigned to just one output, or it has to get assigned to exactly one. Now, it is perfectly fine for two separate inputs to get assigned to an output, right? So like this one gets assigned to that, and this one gets assigned to that as well. As long as we don't have a situation like I'm going to write here in blue here, we don't want a situation such as this to happen, because that means that this one single input gets assigned to more than one and not exactly one output. So we don't want that last situation to happen in order for it to be a function. So there we go. And so usually we call our inputs our x values and our outputs our y values in math. And so I have a set of a couple of tables here with a set of numbers. And in the first set of numbers, we have some x values that include -2, -1, 0, 1, and 2. These are the output values y here. And we have a similar situation here in this table here, except we have -2, -1, 0, -1, and -2. All right. And the question is, which of these represents a function? Well, think about each input getting assigned to one output, right? So here, -2 gets assigned to 5. It doesn't get assigned to anything else because we don't see a -2 here again. -1 gets assigned to 2. Great. It doesn't get assigned to anywhere else because I don't see another -1 here. The exact same thing happens to 0, 1, and 2. So this one is a function. Uh-oh, sorry about that. So this one is a function. While this one here, -2 gets assigned to 4 in this set right here, this ordered pair, but -2 also gets assigned to -2, right? And so as long as I have at least one value that happens for, one input that gets assigned to more than one output, it's not a function. And so in this course, we're going to be focusing on situations like this, where we're only dealing with functions. We're not going to see situations like this because math doesn't have any nice properties when you have this type of situation going on here. Things get very complicated. And so some other terms that are related to functions, we like to use the word domain and range. Your domain is your set of all input numbers. A lot of the people say, oh, it's your set of all x, because we usually use x for input, but you're going to see in this class that we use other variables for input a lot. So it's the set of all x values where your function is defined. And so if I look at this example here, this table that is a function, is going to include the values -2, -1, 0, 1, and 2. Those are my set of input values. And since I'm given a table, I'm just listing the values. I'm not going to say, oh, all the numbers between -2 and -2 and 2. I'm going to just list the numbers that are in my table. The range is your set of all output numbers, and a lot of times in math, we like to use the y coordinate for your output values. And so some people say that the range is your set of all y values where your function is defined. And if we look in this table that we just declared was a function, 5 is in the range because that y value, this -2 gets sent to 5, 2 is in the range, and 1 is in the range. And so my range, if I list the values, I'm just going to list them in order here. I have the values 1, 2, and 5. All right. Now, normally we don't look at functions in this manner in a table, although it's perfectly fine to look at functions in a table. In fact, we're going to use the rule of 4 in this class, and we're going to look at functions in one of 4 ways, and sometimes in multiple of 4 ways, right, in the same problem. We're going to look at them numerically, usually by you looking at a table. All right, so a table of values. We can represent it algebraically using an algebraic expressions. All right, we can look at it graphically. That's kind of self-explanatory. Look at a picture of a function, and we can look at it verbally, sort of like in a word problem. All right, and so we're going to all throughout this semester, we're going to be going from one representation to the other, and in some cases, looking at a function in one representation is much easier to think about quantitatively than looking at it in another situation. And sometimes we're going to go straight mathy on you, and we're going to look at the functions algebraically. And so we're going to see all of these representations. And getting to the algebraic expressions, we got to review some of the notation that involves functions. One of the things I always try to tell students is your output variable is always a function of your input variable. Your output variable is always a function of your input variable. And so if I use y as my output variable and say that that is a function, and if I use my x as my input variable, we say that y is a function of x. And to write that in symbols, a lot of times we say y equals f of x, right? So again, your x is your input variable, your function is your rule, and you apply that rule to your input, and you get your output, which is your y. Okay? Now we're going to change the variables a lot, and so we're going to see in application examples. Usually, if you name the variable with the letter that it represents, the word that it represents start with, it's easy to remember what you're looking at when you're thinking about a function, right? And so let's look at this example. We're going to do a lot of interpretation in this class, a lot of interpretation. And so if you're not used to that in math, get used to it because we're going to do that all semester long. I've had students in the past who have taken calculus and they have excelled very well. They can do a lot of math, but they can't interpret. So one of the things that I want you to get good at is interpreting results and thinking about things conceptually, because we're going to focus on that in this course versus doing a lot of a whole page of just math algebraic manipulation. All right, let's look at this example here to get used to function notation and interpretations. It says the concentration of carbon dioxide in the atmosphere, which is given by, this is functional notation, C equals F of T. The units is in parts per million, ppm. So this concentration of carbon dioxide in the atmosphere is a function of years, which is given by the variable T, since 1960. And so if I look at this notation here, this is my input, T, and my output is concentration of carbon dioxide. I'm just going to say, so this is my output. I'm going to put output there. And so I want to interpret the meaning of F of 40 equals 370 in terms of carbon dioxide. Well, my input variable is T, and T is 40 here, and that's the number of years since 1960. So we could say, and I'm going to type this, we could say, let's say 40 years from 1960, but that, we know 40 years from 1960 is 2000, right? 1960 plus 40 is 2000. So I'm going to say in the year 2000, or you can just say in 2000, my output is 370, and my output is the variable C, which is given here. It's in parts per million, but it represents the concentration of carbon dioxide in the atmosphere, right? And so I'm going to say in the year 2000, the concentration of carbon dioxide in the atmosphere was 370, and I'm going to put parts per million. Now, I really don't know what parts per million is, but that's my units that's given to me in my problem. There we go. We have an interpretation. All right. Part B, what is the meaning of F of 50? Okay. Well, F of 50, right? Well, my F is over here, right? I have an F of 50. My 50 is in here where I see my T, and my T represents the year since 1960. And so 50 years from 1960, that's That's the 50 part. So that represents 2010, because if I add 1960 to 50, I get 2010. But I don't know what this equals. Well, when I see f of something, that means plug it in, and whatever that equals, you plug it in, apply your rule, and the result is your output variable, which is C. So although I don't see C equals, this is basically a C. And a C represents a concentration of carbon dioxide in the atmosphere. And so if I give the interpretation of that, I'm going to say F of 50, 50 is the concentration of carbon dioxide in, okay, now you can see I can't type, in the atmosphere in 2010. That is the interpretation. I don't know how much is in the atmosphere, but that's what F of 50 represents. And there's my interpretation. All right. This is a case of looking at a function verbally, right? We don't have the table of values. We don't have the actual algebraic expression. We don't have the actual graph, but we have some information given to us in words and a little bit of notation. All right. Now let's look at a graphical situation here. It says use the graph of h equals f of t to respond to the following. Label the axes with t and h. All right, well, when we graph, our input variable always goes on our horizontal axis, and our output variable always goes on our vertical axis. And so since our input variable is t, I'm going to label my horizontal axis, like your x-axis, I'm going to label that t, and my output variable is h, and so there's my label for my vertical axis. It says, what is the value of h when t equals 0? T is your input value, right? I go on my horizontal axis and find 0, and then h is my vertical variable, vertical axis variable. I'll give y coordinate, right? At t equals 0, from my origin, we go up to that point right there. If I labeled that, that would be the point 0, 10. So the value of h when t equals 0 is 10. What's the value of h when t equals 3? Well, I go to the right 3 units and find my ordered pair here. All right, this looks a little weird. I'm just going to label this as the point 3, and it has a h coordinate, our second coordinate of 50. So we say h equals 50. All right, what is f of 5 approximately? Oh, f of 5. Notice it didn't say h, it said f of 5. All right, so I go where t equals 5 because that's the t value, right? So f of 5 is going to have this point here. It's an ordered pair with 5 as the input, and it looks dead smack in the middle at 25. So f of 5 looks like it's approximately 25. Now, it may be 24, it may be 26, it may be 24.5, right? I'm approximating, and this is an approximation symbol. It says give the definition of two types of intercepts, right? So we have some ordered pairs on our graph where our first coordinate is the input, the second coordinate is the output. We also can describe our graph by looking at intercepts, right? Intercepts in general are, well, there are two of them. We have a horizontal intercept. All right, now people usually call this the x-intercept, right? You're gonna see that I'm gonna start getting away from using just x and y, right? But your horizontal intercept is the point or points where a function intersects. All right, another word for intersects is crosses the horizontal axis. And then your vertical intercept includes your point where a function intersects, again, you can use the word intersect, the vertical axis. And if you want to say your y-axis, you can. All right. And so if I give the definition of those two axis intercepts, and then we're going to label them on the graph, well, we actually already have our vertical intercept labeled. This is our vertical intercept. is the point 0, 10. And what I want you to notice here is that even if our vertical intercept was not at 0, 10, it will always have an x coordinate of 0, right? That's always going to be the case, right? Because it intersects the vertical axis, right? So we don't go right or left from our origin, we go up or down in order to get on a vertical intercept. So what that tells me is that if I ever want to find a vertical intercept, H2F is how to find. You set your input variable equal to 0, and then you solve for your output variable. So since my input variable here is t, so if I were given an equation or in algebraic form, which you're going to have to do on your homework, I'm not doing an example in class, I want you to review that. You set your input variable, which in this case would be t, equal to 0, and you solve for your output variable, which is h. All right, that is how you would find your vertical intercept. Now, our horizontal intercept on this graph, oh, look at there. Where does it look like it crosses the horizontal axis? Looks like it does it at the point 60 or very close to it. There is our horizontal intercept, right? Notice if I'm going to have a horizontal intercept, I've got to be on the horizontal axis. So from my origin, I can only go right or left. I don't go up or down from my origin, or I will be off the horizontal axis. So the y coordinate, or the second coordinate, is always equal to 0. That gives us a way to find all of our horizontal intercepts. We set your output variable equal to 0, and we solve for your input variable. All right, and that's going to give you your coordinate of your horizontal intercept. All right, so we've looked at a function graphically. Now we can do so much more with the graphs, and throughout the semester, we're going to look a lot at graphs and the properties and how calculus can be used to analyze properties of graphs. Right, that's going to be a huge part of our goal in this course. So what we've done, we've looked at a graphical representation of a function here. We looked at a verbal representation of a function in example 2, and we looked at a numerical representation of a function very simply in this example 1 here. The only one that we have left is algebraically, all right? And so our last example in this video is looking at this function. We have y equals f of x. By the way, y and f of x are interchangeable. All right, they're the exact same thing. All right, that's why we say y equals f of x. Anytime something equals something else, they're interchangeable. You can always replace one with the other. So I could have just wrote y equals x squared, y equals x squared minus 7x plus 13, or I could have wrote f of x equals x squared minus 7x plus 13. All right, but we have this algebraic expression, right? And an algebraic expression involves arithmetic operations with variables. I have a variable x here. I got multiplication, addition, subtraction, and double multiplication, or some more multiplication and an exponent. All right, part A, let's find f of 3. Well, f of 3, that means replace your input variable with 3, right? So I get a 3 squared minus 7 times 3 plus 13. That's 9 minus 21 plus 13. You could have put that in your calculator because we can use calculators in this class. 22 minus 21, which is 1, if I'm not mistaken. All right. Now, when we evaluate like this, basically what we have is we have an input variable, and here we have an output. Basically, what we found is an ordered pair that if we were to graph, we know that this function would pass through. All right. That's what we have here. Part B, find the value of x for which f of x equals 21. Well, f of x is here. We're replacing f of x with 21. Now, f of x is given by x squared minus 7x plus 13. That's the algebraic expression. That's the rule for this function. It takes your x's and you replaces it in this formula here. And we're saying that, oh, when you do that, your result is 21. So what we're going to do is we want to find the x values where such that this does actually, in fact, equal 21. And so we replace the f of x with 21. I just wrote it on the right-hand side, and I solved this equation for x. All right, I want you to think about what type of function this is. It starts with a Q and ends with a C. It's quadratic. There are multiple ways to solve quadratic functions. One of the easiest ways is to factor if it can be factored. One of the things you have to remember is that you have to get everything on one side and 0 on the other. So I'm going to subtract 21 from both sides. Oh man, what does that equal? -8 equals 0. We can factor. This is one of the nice ones that can be factored because there's a 1 in front of this x squared, so I put an x here and an x here. I find two numbers that multiply with a result of -8, but add up to -7. Bam, -8 and +1. So we get two potential solutions, right? So if these two these factors that have a product of 0 actually have a product of 0, then either this thing has to equal 0 or this thing has to equal 0, right? We solve for both of them. We get x equals 8 or x equals -1, right? So those are the x values for which f of x equals 21. There's an alternative way to do this. Some people's favorite, the quadratic formula. All right, so we have x equals -b plus or minus the square root b squared minus 4ac all over 2a, right? When your quadratic function is written in the form ax squared plus bx plus c equals 0, which we have once we subtracted that 21 from both sides, then the a is your leading term, so a equals 1 in this example. B is your linear coefficient, which is -7, and c is your constant term, which is -8. So if I use my quadratic formula, I'm going to have a -7. I'm about to get in trouble. B squared, which is -7 squared, minus 4 times 1 times -8, all over 2 times 1. I actually don't like doing math in my head. All right, so -7 is a +7, plus or minus. That'll be a 49 plus a 32. Get that in my head. All right, -7 squared is -7 times -7, which is 49. And of course, you are subtracting a -32. Subtracting a negative is adding. And it just so happens that this is perfect. That's an 81. So that's 7 plus or minus 9 over 2. That gives me two solutions, right? One of my solutions is 7 plus 9 over 2. And my other solution is 7 minus 9 over 2. That gives me my 8. That gives me my -1, which is the exact same solution I got when I did this over here. Now I'm realizing that you guys probably couldn't see the last little piece that I did, right? Remember 7 plus 9 over 2, that's 16 over 2, which is 8. And then 7 minus 9 over 2, that's -2 over 2, which is -1. And so we get those two solutions there. And that concludes this video.